Hey, good morning, you guys. This is Mr. Ainsworth again, and we are in part three here of our AP Unit 1 review, and I'm just doing a few at a time here. Let's see, I think we ended the last one at number 9, so we're on number 10. So let's find number 10. Okay, so let's go for it here. So for a function pictured, which is greater, the instantaneous rate of change at A or the average rate of change from A to B? So what you need to know on this one here is a couple really important facts that we have learned throughout the last few lessons actually. All right, so the instantaneous rate of change at point A, what we want to do is draw the tangent line. Okay, so let's do that at A. Okay, so remember the tangent line intersects the graph, or that portion of the graph there in this small interval around A at one point. So I'm going to draw the tangent line that intersects the graph at one point. So there you go. There's your instantaneous rate of change at A. We'll call that T1 in our notes. So there's T1, tangent 1. And then we want to draw the, let's see, we want to draw the average rate of change from A to B. And guess what? That is a secant line. All right, because we're talking about 2 points, right? So a line that intersects a function at 2 points is called a secant line. So I'm going to draw that through A and B. And then we'll call that S1, so a secant line. And then we're going to read the question here. So it's if the instantaneous rate of change, we're talking about the slope there, okay, right? So when we talk about that, we're looking at the slope of the line, is greater, go to answer 5. And then if the average rate of change is from A to B is greater, go to answer 25. Okay, so which one's greater? Well, guess what? The steeper one, right? This is steeper, so it has a greater slope. All right, so what we're going to do on this one is we are actually, well, guess what? We are going to go to answer 5. So let's underline that. We got to find the problem with the answer of 5. So I'm going to go up here and try to find, look at those yellow box numbers there, the answers. And we're going to try 5. And so guess what? It's right here on this function here. So we're just on number 10. So I guess this kind of sounds like this was number 11, right? Because after 10 comes 11. So number 11. So let's solve this one. I'm not going to do all of them, but let's just go through as many as we can in a short period of time. So our linear function g of x passes through these 2 points. Find the average rate of change for this function. So what we want to do is understand, all right, that we are on the interval. Okay, wait a minute, on the interval from 1 to 6. Let me think here for a second. So, oh, let's see. So, okay, so it's a linear function. So here's the deal. So we're dealing with a linear function. That is the important thing. Okay, and so it passes through these 2 points. All right, and then it says find the average rate to change the function on the interval from 1 to 6, which is the closed interval from A to B. And what we want to know is that a linear function has what's called a constant, all right, rate of change. So what we want to do is take a look at the rate of change between these 2 points and then go from there. Okay, so let's do that. So the rate of change again is the slope of the line. So the slope of the line, and you guys know that from algebra 1 is y2 minus y1 divided by x2 minus x1. We're talking about the slope or the rate of change. It's the same thing, right? We've been talking that for a while. So because the slope between these 2 points has to stay constant, it must be the same as the slope on the interval from 1 to 6. So all we have to do to find the average rate of change is to figure out the slope between these 2 points. So let's take a look at the y values first, and that's 5 minus 7. So 5 minus 7 divided by 0 minus negative 2. Okay, you get negative 2 divided by 2, or negative 1. Okay, and there's your average rate of change. And the fact that it remains constant over any interval, okay, it doesn't matter whether we pick these 2 points that are given or the interval from 1 to 6, the rate of it's constant, okay? It's constant over all intervals. So constant over all intervals. It's as simple as that. Okay, so now we need to find the problem that has an answer of negative 1. So It's not the first one, it's not the second one, it's not the third one. We got to find the answer with -1. So just keep on scrolling down, and boom, look at this, it's right here. Okay, in the upper right of your screen. So what we need to do there is we need to work on this one. So the family problem. All right, so here we go. We're gonna family friendly food truck has a chicken dinner for a family of 4. That is a lot of S. Okay, Jesus, I have a hard time saying that. All right, so guess what? This is a quadratic function. -1/2 x times 2x, that's a second degree function. So we have a quadratic function here. And what does it want us to do? So it models total revenue. Okay, all revenue functions are quadratic. You're going to learn that in economics. We actually go over that in financial math. All revenue functions are quadratic, and they're all concave down too. And you know this one's concave down because of the negative sign right here. That's probably not pertinent to this problem, but that's just the fact. Okay, and so when X dollars is charged for 1 chicken dinner. Okay, at what price should the chicken dinner be set to maximize revenue? Okie dokie. So at what prices do we, so how do you do this? Okay, so we have this parabola here. This is a parabola. So I'm going to go off to the side here. So this is a basic parabola. It is concave down. Why? Because of this number right here. It's negative, so we know it's concave down. So it kind of looks like this right here. And then so what we want to do is figure out a strategy on how to do this. So I'm going to just draw a sketch here. So let's say, well, let's see here. If we knew the zeros, I'm just going to draw a sketch. So if we have an x-axis here and we draw a parabola that's concave down, and if we knew the zeros here and we're trying to find the maximum, we should know on parabolas that, let me draw a little bit better here. That's a little bit better. Okay, the maximum always divides the parabola into equal halves, and guess what? It's symmetrical about the x-intercepts right here. So we need to find the x-intercepts. This distance right here is equivalent to the distance on the left of the axis of symmetry. So if we knew these x-intercepts, which is when y is equal to 0, all we do is take half the distance and we can figure out where the maximum occurs, because the maximum occurs at the vertex of a parabola, and we just need to figure out this number right here. So let's do that. So here we go. We need to set this baby equal to 0. So -1/2 x times 2x minus 100. Okay, we're going to set it equal to 0 because y is 0. That's how you find an x-intercept in general. And then because of that, you got a 0 product rule. So you kick in the 0 product rule, and well, you just use basically some common sense. You know that something times something equals 0. So either -1/2 has to be equal to 0, or 2x minus 100 has got to be equal to 0. Over here on the left, it should be obvious that x has to be 0. Obviously, -1/2 times 0 is 0. Here, if 2x minus 100 is 0, that means that 2x equals 100, and well, it should be obvious that x must be 50. So if you were to just sketch the graph here, if this was 0 and this is 50, halfway between is 25 right here. So the maximum must occur at 25. So I'm going to write that down. The maximum occurs, okay, at x equals 25, because again, it's symmetrical. Okay, about the axis symmetry, and that's just something, again, it goes all the way back to Algebra 1. It's an Algebra 1 basic. All parabolas are symmetrical about the vertex, which occurs at the max in this case. So if you know that the maximum always occurs at the vertex if it's concave down, because of this negative sign right here, then you just find the x-intercepts, take half the distance, draw the axis of symmetry, which divides into 2 equal halves, and then half of 50 is 25, and you're good to go. Okay, so now what we need to do is, now that we know the maximum occurs at 25, we got to find an answer that is 25. So we got to scroll through this entire document here, find an answer of 25, and then work on that problem. So where, oh, looky here in the upper right. So the answer is 25. So now this is the next problem, and I forgot which one we were working on, so let's look at it. Let's see, which one was it? Where'd it go? Okay, getting a little distracted here. So, oh, here we go. So this one here. So what number was that? I forgot even that. So the previous one, what was that? The previous one was 11, and then we looked for 5. Okay, so 5. Oh God, I'm losing it here. So hang on, sorry. I lost track here. So let me see. 11, the answer is 5. Sorry for the noise in the background here. I got my Great Dane here who's thirsty. I'm trying to find my answers here. Okay, this is great. Okay, I wish I could pause the video, but I can't, so bear with me here. So I think we started on 10. So where's 10? Okay, so 10, we looked for 15. Answer 15, and then oh, there it goes. So there's 10, and then we look for answer 15. Oh, okay. Okay, where'd it go? Can't find it. So might have to rerun this video here because I just can't. Oh, I can't figure out where the answer is. Oh, I'm sorry. Number 10, we go to 5. Okay, so that's it. So number 10, it says go to answer 5. So I'm looking for 5. Holy cow. Okay, so there you go. I just got a little confused right there. So where's the answer of 5? Oh, okay. Oh, there we go. So that's number 11. And then the answer is -1. So then I find -1. Okay, and that's number 12. Okay, so there we go. So this right here is number 12 on so the family food is number 12. And then we have to go to find the answer of number 25, which is 13. So we find 25. We find number 25, and that's 13. Okay, so this right here we go now. Now I'm rocking. This is 13. All right. So the Lafayette problem. So let's take a look at the Lafayette problem here. It's number 13. Let's solve it. All right, and then figure where we go next in the circuit. So the Lafayette here, and I apologize for that, guys, but you know it's late at night and I'm doing this for you, so cut me some slack. Boosters, band boosters, purchased insulated tumblers to sell for a profit. They paid 15 for each tumbler and plan to sell them for $20 each. Okay, if they order 300 tumblers, how many do they have to sell in order to break even? Okie dokie. All right, so the cost is let me see. So let's see, how much per tumbler? So 300 tumblers. They paid $15 for each tumbler, and they plan to sell them for $20 each. Okay, if they order 300 of them, how many do they have to break even? Okay, so they paid $15 for each tumbler. Okie dokie. So what's the fastest way to do this here? So they paid $15 for each tumbler. They ordered 300 of them. So what's 300 times 15? So let's figure this out. So 300 tumblers per tumbler here. All right, and they excuse me. Come on. It's $15 for each tumbler, and they ordered 300. So it should be $15 per tumbler times 300. Come on, Aynesworth. Let me fix this right here. Okay, so let's start over. $15 for each tumbler. They ordered 300 of them. Okay, so you multiply, that's 4,500. All right, total, that's what they spent. Okay, all right, now they say how many do they have to sell in order to break even? So if they spent 4,500 bucks and they sell each one for $20 each, if we take the money spent, all right, and divide that by 20, that should give us the number of tumblers. So if you just do this here and just simplify a little bit, you get 4,450 divided by 2, that's 225 tumblers. Okie dokie. All right, and if you get that, then you get your money back and we're break even. So break even if you sell. All right, if you sell 225 tumblers. So what we want to do is look for the answer to 225 now. So then we start searching. Okay, so it's not below this. So now we start searching, and whatever it is problem number 14. So, oh, here we go. So this is problem number 14. And now we go for it. Okay, I'm going to do one more. So why not, right? So Georgina Orwell wants to fence in her pigs and plans to build a rectangular pen along one side. Plans to fence in her pigs, plans to build a rectangular pen along one side of a pre-existing barn. In this way, she only needs fencing on 3 sides of the rectangle. If she has 400 feet of fencing, what are the dimensions that maximize the area of the pen? All right, so here we go. So let's work on this one. Let's draw a little picture here. So we have the barn here, let's say. So this is the barn. And she wants to put a fence alongside one side of the barn. So here's your fence. So here's the fence in red right here. All right, and we don't know what the dimensions are. So if this side is X feet, all right, this side is X feet, because you know that opposite sides in a rectangle are congruent here. And if she has 400 feet of fencing, which is the total length you have, then whatever left over has to go on this length right here. Okay, so it's whatever 400 feet is, or 400 feet, minus the 2 smaller sides. So it's 400 minus 2x here. And then all of that equals 400 feet. All right, but you want to maximize area, so that's the key. You want to maximize area, and the area of a rectangle is length times width. On this one here, oh, excuse me, let me see. Yeah, you want to maximize area. So what we want to do is calculate the area of the rectangle with this length times width, and that is, the width here is this shorter side. So let's write it this way, width times length. So the width is x and the length is 400 minus 2x here, basic geometry here. And then if you distribute here, the area is equal to 400. Actually, do we need to distribute? Let's see here. No, we actually don't need to distribute. You really don't need to do that. So what are the dimensions that will maximize the area? Hmm. Okay, so again, this is a parabola, right? So again, this is 400x minus 2x squared. This is a quadratic again. That's what you have to realize. And that also faces down. It's concave down. So it's kind of like the previous problem. So here, let's say I want to just draw a little picture here. So if we have this quadratic, it's concave down because of this negative 2x here, negative 2x squared. The lead coefficient is negative. And the maximum always occurs at the vertex right here. This is your max. And guess what? It always occurs halfway between the x-intercepts. So if we found these x-intercepts where y is equal to 0, so let's set this thing equal to 0. then we could solve the problem pretty easily, kind of like the last problem. Okay, so here we go. I'm going to disregard this. I actually don't need this. I'm going to go look at this right here. I know that either x is 0 or 400 minus 2x equals 0 using the zero product rule again. And that means that 400 is equal to 2x, and that means x has to be 200 because 2 times 200 is 400. So we have x equals 200. So if this is 0 and this is 200, then x has to be halfway in between, so the maximum occurs at 100. So the max occurs again, okay, at x equals 100 feet here. And okay, so if x is 100 feet, then the width, let's go up to the picture up here. The width is 100 feet, and then the length, which is the longer side, is, let's see, it's 400 minus 2 times 100, which is obviously 200. So that is the length. And look at this. To advance in the circuit, search for the larger dimension. And guess what? That's the length. Okay? And so the answer here is 200. All right, not 100, but 200, because we want to take the longer side. So then what you do is you go find the answer of 200. So let's do that real quick, and that becomes number, let me see, this problem is 14, so now we look at, the next problem is 15, but it has to have an answer of 100, so let's find it. Excuse me, what did I just say? Let me go back to the problem. It has to have an answer of 200, not 100. So the longer side is 200. So we got to find the answer of 200. And guess what? It is right here. Okay, and that becomes the next problem. And this one we just saw was 14, so the next problem is 15. All right, so let's label it 15, and you guys can take it from here. Okay, and that's all I got tonight because I'm tired. This is Aynesworth. I'm out of here. I'll see you in my next lesson. Bye-bye.